Bismillahirrahmanirrahim. In this video, we will learn about the basic modeling process of a physical system. So we will learn about system modeling. The basic one maybe for this video we only learn about the basic definition, the basic concept of the system modeling, and we will continue to the next video about the modeling process. We will give several examples for you to understand about the basic modeling process. And this is the outline. What will you learn in the system modeling here? The first one is we will give you several examples about mathematical modeling, including mechanical system, hydraulic system, electrical system, thermal system, and pneumatic system. And then we will also learn about the several definition of the system based on the obtained transfer function. We will have first order, second order, and more than that. And also the block diagram. We need to know how to make a block diagram from ordinary differential equations, and then after this class you can formulate a physical system using ordinary differential equation, and then also formulated first order, second order, or more than two order transfer function. And then the third one, you can make a block diagram based on the obtained ordinary difference. So, what is a model? A model is if we have a system like this one. This one is a real world. So you can like give a kind of stimulus, such as maybe I will give you a real case, such as in a tank system we have flow in and also flow out. You can see here if we have Q in a certain change in the Q in, how it will behave. We can see in terms of H, the level. So you will have a kind of data here. Let's say this a time and Q in, and you will have a response, a time response here, like this one. It is only an example. So you can bring this kind of phenomena. You need to recreate. You can recreate, duplicate the phenomena, the behavior in the form of equations. So you will have like a kind of box also, but it is an equation or differential equations. For example, this is dt and so on and so on. Maybe a, b. So we will have this kind of equations. This kind of equation has the same pattern with the real data. Okay. Let's see the formal definition. Model. We will learn about dynamic model, a group of mathematical model representing the dynamic behavior of a system. So we will have a mathematical model. Let's say we have a tank. We like converting this physical system to a mathematical models. For example, it's dh per dt and ah B, Q, in. Yeah. Okay, this one is only example. Dynamic representations expressed in differential equation. This one is differential equation, yeah. We have differential, the derivative parts, and this one is the equation. And also we have independent variable towards time. This one is actually quite a statistical one, yeah. So the independent variables, one of the inputs, or we can say this one, it is a function of time. Yeah. One object can be more than one representation. So actually, if we want to bring this kind of physical devices or convert it to a equation, of course we need several assumptions. Yeah, we need several assumptions, and the obtained differential equations can be different depending on your or the for formulated assumptions. So how do you make a model? We have in general, it is based on Ogata books. We have three methods. The first one is white box. White box, we need to learn it about the white box. This one is based on physical law, yeah. So we can understand that how is the mass balance, how is the hydrostatic equation, how is the continuity functions, and how is the pressure relation with the input, with the flow in, and also mass conversion, and so on. So we built the mathematical model based on physical law. And it is the extreme, another extreme methods. We can use black box. Black box is based on empirical data, so we need to have a data first, then based on the data we can build a mathematical models, and then we can combine both of these methods in a gray box methods. Okay, you will learn this kind of model in your project. In your project I will give you several project, right? So in brief, the modeling process, the first ones, this one is for the white box, yeah, for the white box. Black box has a little different approach. So you need to identify the physical laws, including for the mechanical system, maybe Newton laws, for the electrical system, Kirchhoff laws, and also energy conservation, mass conservation, and so on. And then the second one is you need to identify the variables. You need to determine which one is the output, which one is the inputs, and which one is the disturbance. Then after you identify the governing equations and also the variable identifications, you can building ordinary differential equations, or usually ordinary, but in some case it is not the case, yeah, not ordinary, might be highly nonlinear. And also in other case you need to determine the state space equation. And then after you obtain the ordinary differential equation, you can convert it to a Laplace transformation and transfer functions. And what is Laplace? Laplace is a kind of, we can say, in differential equation, maybe ordinary differential function is about time domain. And for the Laplace, it is a kind of frequency domain. If you want to learn further, deeper about the Laplace transformation, there are several literature I can give you. But if you don't want, it's okay as long as you can convert the ordinary differential equation to a transfer functions. Another definitions. We have linear and versus nonlinear. What is it? In linear, there are several rules you can apply, like superposition principle can be applied, such as this one, and also, so if you assume a system is linear, you can use a percentage to model the system. And also, accurate or valid in a quite narrow operating range. So, in real-world applications, the majority of the system, the majority of natural system is highly nonlinear. So, if we want to model in using a ordinary differential equation or transfer functions, we need to linearize or we only observe in a kind of a narrow operating range. And also, usually, coefficient for the output equation is constant because it is linear, yeah. And the nonlinear is the opposite. I think you can understand this one after you done deeper or you want to take final project or maybe independent project with me. You can understand these two terms deeper, yeah. So how to convert nonlinear to linear equation? There are several methods. Two of them is this one, Taylor series expansion. Per two batching approach, or it is a kind of observing only a narrow operating range.